Hello students, this is Mr. Maat with another physics lesson. In this chapter sound, we're talking about sound waves. And the first thing that I want to do with you is to view at two simulations from Phet, Colorado, where we can actually adjust the properties of a wave. We're going to experience, well, how that changes the sound, and you can adjust everything that you like. After that, we're going to focus on some theory. We will talk about some properties like amplitude and wavelength, and I will also come back on high and low pressure. For next lesson, you need to make sure that you finish this complete lesson with all the assignments. Okay, if we're talking about sound, we're actually talking about vibrations, waves in the medium. A medium is actually a bunch of molecules, and those molecules, they start vibrating as soon as a sound wave hits those molecules. It all starts with a source. If a source starts vibrating, it causes all the air molecules in front of it to actually start moving. At a certain moment, well, you have the receiver and it picks up the sound wave and converts it into a sound. Well, it all starts with a vibration, so it's important that you understand what the definition is of a vibration. A vibration is a movement around a fixed point. So we're talking about those molecules, and they come back to their fixed position at a certain moment when the sound wave is not traveling through that medium. We also call that a to and fro movement. That's exactly the same as just a vibration. Okay, let's start with the first simulation, and it's a simulation of Phet, Colorado. You can open that yourself. I will post a link later on in the movie. Well, I'm going to adjust a couple of things. I want it to constantly move. I don't want to have something at the end. So here you see a wave. And it's actually a long string, and you see all those molecules in the string. Some are highlighted with green, but they are exactly the same. It's just to give you a clear view what actually one molecule is doing. So let's adjust the frequency a bit. I'm going to make it a bit less so that I get less waves in 1 second. So the frequency tells you something about how many waves there are in 1 second. The more waves, the higher the sound. And I will show you that later on in a different animation. But the thing that you need to focus on are the frequency and the amplitude. I will make sure that this one is set on 0. And well, sometimes it's helpful to have some kind of a guideline how big the waves are. So there are two things that you can adjust. And that first of all is the frequency. So if I add more hertz to it, you see I get smaller waves, and the waves it seems that the waves are still the same size in height if you make this frequency lower or bigger. That doesn't matter. So the height of the wave is something that you can adjust as well, and that is the amplitude. So if I adjust the amplitude, I can actually make the wave smaller. The frequency, the amount of waves per second is still the same, but the amplitude, the volume of the sound is going to increase if I make those waves bigger. Well, an important thing to see is that this green molecule over there is actually only moving in the vertical direction, up and down, up and down, up and down. But the wave itself travels from the left to the right. So it's important that you understand that the molecules are not traveling in the same direction as the sound. The sound travels to the right, and the molecules in this case, they travel up and down. So make sure that you understand that the molecules are not itself flying through towards your ear. That is not going to be the case. So, and because those molecules are all attached to each other in some way, then you get the vibration through the air. So I hope that you can play with this animation yourself at home. It's just a website, and the simulation will run on that website. So let's go back to the presentation. Here's the presentation again. And last lesson we also talked about high pressure and low pressure regions. And that has to do with the amount of molecules over there. So if there are a lot of molecules very close to each other, we say it's a high pressure region. And most of the times you will get a top of the sound wave over there. With low pressure, well, it's just the opposite. There are just less molecules, so the graph will be at the bottom. So the particle always starts moving from its neutral position, and it moves to the position A and can move to position B. Again, in the simulation, they did it vertically, so it moved up and down, up and down. Well, that's actually just the same. Well, the amount of distance that the particle moved tells you something about the volume of the sound. So we call this distance, we call that the amplitude. Well, that is of course the same on the other side. So it doesn't matter where you measure the amplitude, it's everywhere the same for that particle. So the amplitude is something that we can study, and I'm going to show you how you can adjust the amplitude in the next simulation. So again, a simulation of Phet, Colorado. And let's start the animation. There are 3 different screens that you can choose: water, sound and light. It all has to do with waves, of course. Well, we're talking about sound, so I'm going to open this simulation. What you see over here is I have a speaker over here, and that is of course my source. It can actually start vibrating and creates a sound wave. Well, over here I can switch on the particles, and you see those particles are always moving just a tiny bit around that neutral position. If they would stand still, well, we would have reached the absolute zero, but that is of course not the case. Okay, now let's switch on this speaker, and it creates a certain sound. You see that over here, the waves travel actually through that material. Well, now switch on the sound as well. Here's the sound. So if I also put the waves in like this, you can actually see that the sound wave is actually spreading through that material. And you see that the molecules are constantly bumping into each other. Well, now we can adjust the frequency and the amplitude as well, and we can actually see and hear what is happening with the tone. So let's switch on the sound again, and I'm going to play first of all with the amplitude. The amplitude tells you something about the loudness of the sound. And you will see that the louder the sound, the more those molecules start moving back and forward. So let's adjust the amplitude. I put it almost on 0. And now I'm going to switch on the sound, and of course in the beginning you won't hear anything. Now I'm going to increase the amplitude. And you will see that the molecules start moving faster and faster. What is important to see is that the amount of waves that you see over here in the simulation isn't going to change. The amount of waves stays the same, but the amplitude is changing, and that makes the volume louder. So now I'm going to adjust the amount of waves that you see over here per second, and that is actually the frequency. So I'll put the amplitude again somewhere halfway, and now I'm going to play with the frequency. So I will switch on the sound, and first I will start with a very low frequency. So less waves per second, and then I will go up to a maximum frequency, a lot of waves per second. Let's switch on the sound. Low frequency, still the same amplitude, the molecules move in the same way, but the frequency is going to change, so the amount of waves is going to change. And you hear the sound getting higher, so that's an important thing to remember. The higher the sound, the more waves you have per second. So let's go all the way up. So now I can adjust, of course, the frequency and the amplitude, and you get this kind of effects. Maximum frequency, maximum amplitude. I'll make the amplitude smaller, so then you will get a tone that is less loud. So this is the other simulation, and I want you to start playing with the simulation yourself. Try it at Phet, Colorado. Okay, a bit of theory. It's important that you start drawing sound waves, and drawing sound waves isn't that easy. So there are a few spots that are always easy to remember and, well, actually to set out if you want to draw a graph. So what I want you to do, I want you to draw a vertical and a horizontal axis, and we're just going to place some dots. The first dot that you need to place is this one over here, and you just put it on 0. The next one, you go 3 centimeters to the right, and you go 3 centimeters up, and you play that second dot. Well, then the distance over here is again 3 centimeters. So the total distance from this point on to that point on is going to be 6 centimeters. So the top of this first wave is actually going to be exactly in the middle. Well, the same over here. This distance is again 6 centimeters, and you drop 3 centimeters downwards. The distance between this point and that point will be 6 centimeters again. Well, if you place all those dots, then you take your pencil and you start at the 0 and try to draw a really nice fluent line. That's the way to set up a good sound wave. Well, you already saw that I mentioned this distance, and that distance actually tells you the amplitude, so how loud the sound is. So the larger this value, well, the larger the sound and the more volume that you will experience. The same is over here, so don't think that this is going to be a negative sound or something like that. It's just that the particle moves upwards and it moves downwards. And if you plot it in a graph like this, well, you actually get a sound wave. So the amplitude is the maximum displacement with respect to the equilibrium position. So the equilibrium position is of course this axis, and it's the maximum displacement from that equilibrium position. Amplitude is something that we can study, it's a quantity. So the standard abbreviation for amplitude is a capital A. Don't get confused that you think that this is the same one as the one for the surface area, because that is correct, but you always need to take a look at the unit. And the unit for the surface area is of course squared meters, and this one is decibel. Lowercase d, capital B. So the amplitude tells you something about how loud the sound is. Well, we saw in the simulation that the frequency, the amount of waves per second, tells you something how high the tone is, about the pitch. Well, that of course is related to, well, how big the wave is. If you would measure the wave from a top to a top, you're actually talking about the wavelength. So how long is that wave? Well, low frequency sounds, they have a very big wavelength. High frequency sounds, they have a really short wavelength, because the frequency is getting higher as well. So, the wavelength is actually this. It's the distance between two consecutive points. So it doesn't matter if you start over here and end up over here. You can also start over here and end up over here. That is called the wavelength. Well, the wavelength is of course measured. And lambda is a symbol for wavelength. And, well, the standard unit for wavelength is meters, but believe me, sound waves are extremely small, so sometimes we talk about nanometers or something like that. Okay, for next lesson, I want you to finish this whole lesson. Make sure that you do all the assignments. I hope you enjoyed this movie, and see you soon. Bye-bye.